Right now, across your entire vascular system, liver, and digestive tract, billions of individual cells run their own autonomous clocks. They pulse, metabolize, and rest in a continuous rhythm synced perfectly to the Earth's daily rotation. These autonomous cellular clocks cannot function independently. Without a centralized metronome, individual rhythms drift out of phase, leading to desynchronized metabolic and digestive cycles throughout the body. That metronome is the suprachiasmatic nucleus, or SCN. It sits at the base of the brain, directly over the optic nerves. It's a discrete cluster of 20,000 neurons within the anterior hypothalamus. This is a small footprint for a system coordinating trillions of cells. To control the entire body, a central clock might be expected to have widespread neural projections weaving throughout the nervous system. In reality, the SCN projects almost no direct neural wiring to the broader brain and none to the peripheral body. Its influence is managed through a localized, top-down neuroendocrine pipeline. The SCN creates an anatomical bottleneck by concentrating its neural and chemical outputs into a few specific, immediately adjacent zones in the hypothalamus. The system relies on this structural bottleneck, condensing environmental time into a single perfectly positioned chemical trigger. The process begins when environmental light strikes the retina and converts into an electrical impulse that travels direct to the clock. This delivery highway is the retino-hypothalamic tract, which feeds continuous light and dark data into the SCN. The SCN restricts its outward communication, relying on autonomic neural pathways and specific neuropeptides to signal only its immediate neighbors. The primary chemical messengers used here are vasoactive intestinal peptide, or VIP, and arginine vasopressin, known as AVP. These peptides target the DMH, or dorsomedial hypothalamus. The DMH acts as a rounding hub for behavioral states, coordinating sleep-wake cycles, feeding routines, and core body temperature. The second target is the PVN, or paraventricular nucleus. The PVN is a massive integration zone for autonomic and endocrine functions. SCN projections here dictate the daily rhythms of stress responses and thyroid function. Finally, the SCN wires into the MPOA, the medial preoptic area, to regulate reproductive cycles and core temperature fluctuations. The SCN translates light into localized chemical instructions, aligning the behavioral, autonomic, and reproductive hubs of the hypothalamus to a 24-hour cycle. The signal now moves geographically downward to the pituitary gland. Because the pituitary gland sits downstream, the SCN's upstream tining forces the hypothalamus to release signaling hormones, which in turn gate when the pituitary secretes trophic hormones into the bloodstream. We can trace this pipeline through the HPA, or stress axis. This chart graphs the resulting hormonal activity over a 24-hour period. During sleep, the SCN sends an inhibitory GABAergic signal directly to the PVN, keeping the stress axis closed. As morning approaches, the SCN lifts this inhibition, allowing the PVN to secrete corticotropin-releasing hormone, or CRH. CRH hits the anterior pituitary, triggering ACTH release. This causes the adrenal glands to flood the body with cortisol, right as you wake up to mobilize energy. A parallel timeline governs the HPT, or metabolic axis. Here, hypothalamic TRH guides the anterior pituitary to release thyroid-stimulating hormone, or TSH. The TSH curve is inverted. It peaks at night, typically between midnight and 4 a.m., and hits its lowest point in the late afternoon. This midnight peak aligns systemic cellular heat production and metabolism with the body's resting state. Through the PVN intermediary, the SCN acts as a systemic floodgate, selectively holding back or releasing chemical energy shifts to match environmental rotation. Moving from the PVN to the medial preoptic area reveals how the SCN controls the HPG, or reproductive axis. While the hypothalamus naturally releases GnRH in a baseline pulse, the SCN superimposes a 24-hour circadian rhythm over it. This is visible on the timeline as a synchronized peak that sits on top of the baseline pulses. In spontaneous ovulators, this timed signal from the SCN to the MPOA is required to trigger the surge of luteinizing hormone from the pituitary. Without this top-down gating, ovulation fails to trigger even when baseline hormone levels are normal. The final major output in this cascade involves growth hormone and prolactin. Unlike the other systems, growth hormone release is tied to deep sleep stages rather than direct light processing. However, the SCN still controls the timing by manipulating both the inhibitors and activators in the hypothalamus. It manages the release of somatostatin, which inhibits growth hormone, and GHRH, which stimulates it. By timing these signals, the SCN ensures a surge of growth hormone occurs immediately after sleep onset to facilitate tissue repair. This restricts reproductive viability and cellular regeneration to specific, predictable daily windows. Pulling back from the neuroanatomy reveals the architecture of circadian control as a single unified system. The functional architecture is a strict top-down cascade. Light translates via the retina to the SCN. Localized chemical signals hit the hypothalamic nuclei, the PVN, DMH, and MPOA, triggering releasing hormones. These force the pituitary to release trophic hormones, ACTH, TSH, and LH. Finally, these endocrine floods wash over the peripheral systemic organs, forcing them to sync to the central clock. This tiny cluster of 20,000 neurons manages the timing of trillions of cells without needing to wire to each of them directly. It exerts total control by utilizing its position as a bottleneck, restricting its output to the highest leverage triggers in the brain. The suprachiasmatic nucleus aligns metabolic, reproductive, and stress response activities to the 24-hour rotation of the planet through localized, top-down neuroendocrine delegation.